Okay, guys, let's get our videos on. Let's get our videos on. Let's get our video. Most must be attending by Zoom today. Most must be attending by Zoom. Get out of the way. Let me get out of the way. Scribe. You guys can scribe. I'll read while you guys write down. In class, it's a lot easier to see. R prime of C by definition, R prime of C by definition is equal to the limit as t approaches C of R of t minus R of C over t minus C. Where R of t is a vector valued function, what does it mean to be a vector valued function again? What's the definition of a vector valued function? You have what on Friday? You have what on Friday? Quest. Which sections? Which sections? 13.1 and 2. 13.1 and 2. Will there be proofs? Will there be proofs? No, there will not be proofs. Will there be definitions? Will there be definitions? Did you guys get my email? Did you guys get my email about the flashcards? Did you guys get my email about the flashcards? So there isn't as many flashcards. They're just more to memorize, guys. They're harder to memorize. They're harder to get down. It's really easy. It's really easy if you guys don't have them down to trick you. It's really easy to trick you, even though there's not as many. And it's my job to trick you. What's the definition of a vector valued function?
Ordered triple of 3 real valued functions.
Perfect, Roberto. Perfect. It's an ordered triple of 3 real valued functions. So like, for example, right here, R of t is equal to the ordered triple of the real valued functions
Y of t, z of t.
z of t. And I'll use little x, little y, little z. Okay, this is a theorem. This is a theorem. We almost never use the definition of the derivative when calculating derivatives. We almost never use the definition of the derivative when calculating derivatives, because we have a theorem that says that if you want x prime of c, all you need to do is take the derivative of x, take the derivative of y, take the derivative of z, and plug c in. That's one of the theorems that we proved. But guys, in applications, it's the limit definition that comes into play. If you want to memorize formulas and regurgitate stuff back on test and have that be your total understanding of calculus, that's fine. But if you actually want to use it in an application, you're going to have to remember the actual limit definition. In the same way, the integral of a vector valued function, the integral from a to b of R of t dt, now you guys read this off because you haven't seen this as much, is equal to the
Limit
as
and approaches infinity.
of the sum as k goes from 1 to n of the function
R
evaluated at times
delta t.
delta t. This is complete crap right now until you explain who that guy is and that guy is, where
Delta t equals b minus a divided by n.
so we're taking our interval, we're taking the axis we can't plot, t, we're taking a and b and we're chopping that interval into n parts. And my t sub k's are as k goes from 0 to n. As k goes from 0 to n. This is the definition. This is the definition. This is the Riemann sum. This is the Riemann sum definition of the integral of a space curve. Now what we did in class last time is we justified a theorem that says, oh, the integral of this vector valued function is nothing more than the integral of each of the real value functions. So if my function is an ordered triple of 3 real value functions, then the integral of my vector is nothing more than the integral of my components. But that's a theorem, it's not a definition. Imagine you saw this on the quest. By definition, this integral is equal to this vector. Would that be true or would that be false? By definition, is this integral equal to this vector? And the answer is false. By definition, it's equal to this limit, which just happens to be equal to this vector by a theorem. Again, in application, we don't want to use Riemann sums. If at all possible, we want to use the fundamental theorem of calculus, which says, hey, Dr. Warren, if you can find a function whose derivative is this guy, and you can find a function whose derivative is that guy, and you can find a function whose derivative is that guy, then you can do this integral by just doing x of b minus x of a, capital X of b minus x of a, capital Y of b minus capital Y of a, and capital Z of b minus capital Z of a. So let's imagine that I can find these functions. Imagine that I can find a function capital X, I can find a function capital Y, and I can find a function capital Z that obey what I need in the fundamental theorem of calculus. Capital X prime is little baby x, capital Y prime is little baby y, capital Z prime is little baby z. Then what would the derivative of this vector value function capital R be? What would the derivative, using our derivative theorem, what would the derivative of capital R be? Would be the derivative of capital X, capital Y, capital Z, but the derivative of capital X is equal to, the derivative of capital X is equal to
X.
little x. Similarly there, so we get the derivative of R, capital R prime, is equal to x, y, z, little baby x, little baby y, little baby z. But that vector is equal to little r, and so we get this beautiful extension of the fundamental theorem of calculus to vector value functions. That the integral from a to b of little r is equal to capital R of b minus capital R of a, where capital R prime of t is equal to, or capital R prime of t is equal to little r of t. This beautiful extension of the fundamental theorem of calculus to vector value functions. So you're looking for a vector value function whose derivative is, I'll keep going. You're looking for a vector value function whose derivative is little r of t. So imagine you're facing this. You've got the integral from 0 to 3 of this vector value function. How many people think they could find that? How many people think they could find the integral of that vector value function? How many people think they could find the vector that represents the integral of this vector value function? How many people think they could do that? How many people think they could do that? Because you're going to have to do it on a quest. You're going to have to do it this Friday on a quest. You're going to have to do this Friday on a quest. So try it. Try to find the integral. It's t cubed, the integral from 0 to 3 of t cubed sine t and the square root of t. Try to find the integral of that vector value function. David, how are you feeling, man? David, how are you feeling? That's what I want to hear. That's Stuart, so good to see you in the room. Now, on Friday, you're gonna be allowed 40 minutes only. You're gonna be allowed 40 minutes. I'm cutting the class essentially in half. You should be done. You should be done on Friday. By now, you should be done. Let me give you some cheating ways to help you. Okay, so if I'm looking at this, I'm immediately gonna say, can anybody think of a function whose derivative? Can anybody think of a function whose derivative is t cubed? And nobody in class can do that. Can anybody think of a function whose derivative is t cubed?
1/4 t to the
1/4 t to the fourth. So you guys on Friday, for sake of time, in this class, you can just write this as t to the fourth over 4, put a line, and put the number 0 and 3. I don't need you to do the arithmetic. You can leave it there. The calculus is done. Now I need a function whose derivative is sine.
negative cosine.
Negative cosine. Evaluated between 0 and 3. I don't need you to do the 0 and the 3. You have no calculator on Friday. Okay, how do you integrate square root?
Minus the top thing and then bring it down.
So this is the same thing as t to what power? 1/2. Add 1 to 1/2. 3/2. So it's going to be t to the 3/2 divided by 3/2, power rule, evaluated between 0 and 3. You're done. You leave it like that. Put a box around it, call it gone. Okay, let's go back to Math 236. And you're like, no, Dr. Warren, let's think about some of our integration techniques. Luke, what was one of our integration techniques from 236? Luke, are you there, Luke? Are you there, or are you hiding out? Did you just turn off your camera and you're not really there? Cameron, what was one of our integration techniques?
Luke said his microphone is not working in the chat.
Okay, thank you. So Cameron, what was one of our integration techniques? Sorry, Luke.
I don't recall.
Okay. Ava, how about you? Ava, can you remember any of our integration techniques? My wife's gonna be pissed, man. Ava, can you remember any of our integration techniques?
Probably yes, but I'm not good on the spot, so not right now.
Okay. But Ava, you are so good on quests.
Luke says trig substitution.
Trig substitution, thank you, Luke. From the balcony, okay. Now in class, can you give me another one, Mason?
Not at the moment.
Not at the moment, Zach. Michael? UDU, what that's called? U substitution. You guys remember U substitution? Do you guys remember U substitution? Like, for example, if you had the integral of e to the t squared TBT, what would you let u be? What would you let u be? Oh shoot, Dr. Warren, it's been a whole summer. You let u be equal to t squared, then du would be equal to 2t dt. Is stuff coming back to your brain? Okay. Do you guys remember trig sub? You're like, no, don't hit. Partial fractions. Powers of trig functions. Okay. Guys, in this class, if it's not homework and it's a quest, the most I will hit you with is a U sub. I'm not going to test your integration techniques as much as your vector calculus stuff. Are you okay with that? Will you have to know U sub? Yes. Okay. All right, stand up. Stretch. Luke, you stand up. Thanks for that, getting that. Gordon, you better be standing. Oh, where's Bridget? Okay, let's sit back down, let's sit back down. Okay, draw an XYZ. Draw an XYZ. Give yourself an R of t, but don't make one up, just leave it as R of t. Let's give ourselves a vector valued function. And give ourselves a domain, let's make it what we have, a to b. T is an element of a to b. When I say line, you say,
A plus TD.
when I say plane, you say
And, X minus A equals 0.
0. Okay, when I say tangent line, you say, when I say tangent line, you say, by Friday, you say,
R of t plus t, R prime t.
very good, close, Gordon. It's R of C, little vector R of C plus T times R prime of C. That's the tangent line at the point R of C. So I say tangent line, you say,
R of C plus T, R prime C.
very good, Mason, only Mason. When I say tangent line, hands on the space bar, hands on the space bar, hands on the space bar. When I say tangent line, you say,
R of C.
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 so what's R of C's job in this tangent line? What's R of C's job in the tangent line?
The position vector.
Very good. The position vector. What's R prime of C's job? Direction vector. Direct. It lies on that line. Okay. Stand up again. You're gonna need this. You're gonna need this. You're gonna need this. Stretch. We're going on a long adventure. Look at your clock. Look at your clock. Look at anything that tells time. What time is it? What time is it? What time is it?
10:03.
Okay, what time does class end?
11.
11. Okay. 11. We will not be done till 10:45 with this. We will not be done till 10:45 with this. Sit back down. Draw yourself a space curve on that XYZ. Draw yourself a space curve on that XYZ. Okay, so I've got a vector valued function. A vector valued function is a ordered triple of
3 real values.
3 real valued functions. My domain of this vector valued function is
A to B.
A to B. Which axis is not plotted? The t-axis. I don't have any axis for my domain. Now I'm gonna plot my range. And geometrically, what is R of t? Geometrically, what is R of t?
Space
A
curve.
space curve. So I'm gonna draw myself a space curve in 3-dimensional space. Oh, maybe I'll- something like this. Okay, now I can imagine that like maybe this vector here is R of A. When I'm starting, my position vector R of A is pointing to that point on this curve. And then when I'm over here, I'm imagining that this is R of B when I'm at the other endpoint. So which way am I going on the curve? Which way? If I've got to mark to the audience, which way would I draw my arrow? Which way would I draw my arrow on the curve?
Towards the left.
Yeah, it's swinging this way, it's swinging this way in three-dimensional space. Now, it'd be fun if we just had, if I had more time, I would have each of you pull out your laptops here, everybody at home, pick a space curve and plot it. That's what I'd have you do. I'd give you the domain, you guys would have your own unique space curve, and you'd plot it in that routine. Let's pretend we did that.